I'm Anil Kumar, and in this particular video, I'll take up implicit differentiation. This video is for all students who have already learned basic rules for differentiation, including the chain rule. Now, we'll talk about implicit differentiation. Till now, you had been working with functions which were explicitly written in terms of x. For example, you always were working with f of x, right? When we say y equals to something, that function was in just x. Perfect. That is what you had been working with. However, you have seen many equations which could be written with combination. For example, you could write x squared minus y squared equals to 10, for example. Now, in this particular equation, you have both x and y terms. Now, at times, it is easy to write y explicitly in terms of x, right? So that is what we mean explicitly. That is to say, when you can isolate y, right? So in explicit functions, we could isolate y, right? And get the equation. But at times, if we have some equation which is slightly more complicated, for example, if I have x minus xy squared plus y cubed equals to something like this, it may become very difficult for you to isolate y, right? It is sometimes difficult. So in that case, how do you find derivatives? That is what we are going to understand. And to find derivatives, we basically use the chain rule. So I'll take a few examples where we'll go in steps to understand what is implicit differentiation. And the first person to solve this had a problem from Descartes and the equation was x cubed plus y cubed equals to axy. So this is a very interesting equation to take as an example. Here it is kind of difficult to isolate y, a is a constant. And so it was a challenge for one of the mathematicians who just introduced a concept of finding tangent line slope for any curve, Fermat. And Fermat actually gave him the solution, and that solution is what we follow today as implicit differentiation. So that's kind of history. Now let's begin with some simple equations. Equations here are xy equals to 6, x squared plus y squared equals to 6, x cubed plus y cubed equals to 6xy. So here this equation, I've replaced the constant a by the value 6, right? Now these equations, when written like this, if you rearrange and isolate y, for example, in the first equation, we could write y as 6 over x. In the second equation, we could write y as, let me write first y squared as 6 minus x squared, and then y as square root of 6 minus x squared. And whenever we square root, we do plus and minus. And here it is kind of tricky, and I will say at this stage it is difficult to isolate y. And that is why it was a challenge to find the slope, because whenever we find derivatives, we are in a position to write our function as in one variable. Do you see that part? So here we have to find derivative when two variables are involved. So that makes it difficult. Perfectly. So these derivatives were easy. You could easily write down, you know what y dash is here. Since this is x to the power of minus 1, the derivative is minus 6 over x squared. Here also derivative is not all that difficult. However, you will see that this is not a function, right? Likewise, that is also not a function. So many times you may be asked to find derivatives for relations represented by equations, of course, which are not functions. So when you are working with two variables, that can happen. Here, circle is not a function. Similarly, this is also not a function. So if you sketch, this function will be kind of like this, a circle, and this function is kind of interesting. It is equal to, something like this. The leaf here, right? So something like this. So that is what this function is, correct? So if I draw the axis, this function will be kind of like this, and here at the origin there is this axis is there, correct? So that is how the function may look like. So as you can clearly see that this curve doesn't represent a function, as it fails a vertical line test, just as circle fails a vertical line test. Perfect. But the question is, how do we find equation of a tangent line for such a curve, right? For example, if I take a point here, we can obviously draw a tangent here. Perfect. So we could have a tangent here which will look like this, and you can estimate the slope of this tangent. Perfect. But how do you find it mathematically, algebraically? That is what we'll see with the help of implicit differentiation. So I hope you understand and appreciate the importance of implicit differentiation, right? So when it becomes extremely difficult to isolate y, and we have to work with both x and y, we perform what we call implicit differentiation, correct? So let's move on, and let's work with, as I said, extension of chain rule helps us to find implicit derivatives of functions. So I've taken up an example here. It says, find equation of a tangent line to the semicircle. So I've taken semicircle simply because I want to show you with functions. So I don't really want to complicate the things so much at this stage. So let us say this is the semicircle of radius 5. So let's say this is the radius 5 for us, and there is a point which is 3, 4. Correct? So this is what we're talking about. So that is x-axis, this is y-axis. Find equation of tangent line to a semicircle with radius 5 centimeters at a point 3, 4. Let's call this point P. So the equation of this semicircle is x square. Okay, let me write y. I wrote first. Y square plus x square equals to 5 square, where we know that y is greater than equal to 0, since we are only taking the upper half, and that makes it a semicircle. Also a function. Perfect. Now you could always find the derivative by isolating y and then working it out. Now we will, for a moment, get back to the chain rule, right? And then find the derivative using the modified method. Now this is easy. If you could do it with square root functions, you could do it. But I want to introduce you to implicit differentiation, and that's the reason why we will actually deviate from our normal. So normally what we say is that if we have a function, let us say, let me write another function here, f of x whole, let me say, to the power of 5, right? So what is the derivative of this function? Let me call this function as some capital F. What is the derivative of this function? Applying the chain rule, you say it is 5 times all this, which is the function, 5 minus 1, which is 4, times derivative of, you say, derivative of inside function. Do you see that? Derivative of inside function. Correct? Now that is the concept. Now here again, y is same as f of x. So in this equation also, I could isolate y and write it as f of x. So the derivative of y squared will be 2y, power will be 1, times derivative of y, y dash. Do you get the idea? So let's follow this strategy which we just now learned, and then find the derivative. So now we will differentiate. We said D for differentiate with respect to x on both sides. So what do you get? 2 times y times y dash. Do you see that? This is this y dash, derivative of this, applying the chain rule. And for 2x, differentiating with respect to x, we get 2x, and that is a constant. We get 0. And now we can isolate y dash. So we can say 2y is equals to minus 2x. 2y dash is equals to minus 2x. And 2 cancels, or we can say y dash equals to minus 2x over 2y. And that gives you minus x over y. Correct? So what you get here is the derivative as minus x over y. At a point 3, 4, we know the value of 3 and 4. So we can say that the derivative or slope at x equals to 3 is what? The point 3, 4, and y equals to 4 is what? We can replace this and we say minus x is 3, so it is 3 over 4. So that becomes the slope of the tangent line at this point. So at this point, if I sketch a tangent, I know that the slope of this tangent is going to be negative 3, 4. Correct? So that becomes the slope of this line. Now once I know the slope, so did you see how without isolating y in this equation, I found its derivative. And this fashion of finding derivative is implicit differentiation. Do you get the idea, right? Now, we can always find equation of tangent line. So we say let it be y equals to mx plus b. And we know the slope is minus 3 over 4. So it could be this. Substituting the values 3 and 4, we get 4 equals to minus 3 over 4 times 3 plus b, or b is equal to 4 plus 9 over 4. Correct? Taking it to the left side, 4 times 4 is 16 plus 9 is 25 over 4, right? 16 plus 9 is 25 over 4. So we get our equation y equals to minus 3 over 4x plus 25 over 4 in slope-intercept form. Do you get the idea? So we got the equation without isolating y. That's the beauty. So till now, you found the equation of this, equation of a tangent line by first writing this equation in terms of y. That is to say, first you wrote what y is. You wrote y equals to square root of 5 square, which is 25, minus x square. Since we're talking about positive part, you will take positive part. And then the derivative, you get the result, correct? But this time we found it without that. So if you check, you will get the same answer. And this method is called implicit differentiation. So I hope the method is clear to you. Perfect. Now let's take a few more examples. Now we are going to apply the technique learned of extending chain rule and finding derivative of relations without explicitly writing the equation in terms of one variable, right? So the examples here, we have 2 of them. We need to find derivative of y by implicit differentiation. First one is square root of x plus square root of y equals to 4. And then we have y square plus x square equals to 2xy. We'll use Leibniz notation here. Since that is, that gives you exactly you are differentiating with respect to what, correct? So let us differentiate with respect to x on both the sides. So basically, we want to find d dx of square root x plus d dx of square root y, which should be equals to d dx of 4. Now d dx of square root x is 1 over 2 square root x. That of y will be 1 over 2 square root y dy dx, correct? Derivative of inside function, which is y. And derivative of a constant is 0. We need to find dy dx, so let's isolate it. So what do we get here? We get 1 over 2 square root y dy dx as equals to minus 1 over 2 square root x. You could always cancel 2's. Let me rewrite this as dy dx equals to minus cross multiply 2 square root y over 2 square root x, which is minus square root y over x. Correct? So we have found the derivative of the function without writing explicitly in terms of y. Do you see that? So you could write y dash as negative square root y over x. The second one here is y square plus x square equals to 2xy. Let's again do differentiation with respect to x on both the sides. That is to say, d dx of y square plus d dx of x square equals to d dx of 2xy. Correct? So this is, apply the chain rule. 2 times y is the derivative times derivative of inside function, which is dy dx. Correct? Here we get plus 2x equals to. Now we need to apply product rule here. You could consider 2x as one of the functions, the other one will treat as y, right? So product rule means, let's revise, if we have to find product rule derivative, that means that is a function, right? So if that is your function, let's say y equals to this. In that case, y dash is u derivative v plus u times v derivative, correct? Now we are considering 2x as the first term, so derivative is 2 here, times y plus 2x times derivative of second function, which is y, which is dy dx. Perfect. Now we can isolate dy dx, bringing it to the left side. You can also cancel 2's, right? So let's cancel these 2's, right? Now what do you get? You get y times dy dx minus x times dy dx equal to y minus x, okay? Bringing that. So dy dx is a common factor, so we can write this as y minus x times dy dx equals to minus x. Dy dx in this case is going to be y minus x divided by y minus x, which is equal to 1, correct? So that is the derivative of the function in this particular case. So you can always find derivative even without explicitly writing an equation in terms of a variable, correct? So let's move on. Now here is a challenge question for you. We need to find derivative y dash to Folium of Descartes' equation, which is x cube plus y cube equals to 6xy. As I've given you a background on this history, this is from where the implicit differentiation started, right? We'll also find the equation of tangent to the above relation at 3, 3, and we'll find the points where the above tangent is horizontal. So I might run into 2 pages doing the solution of this equation. Let's begin by writing the equation itself, which is x cube plus y cube equals to 6xy. Differentiating both sides with respect to y, differentiating both sides will differentiate with respect to x. So right, differentiating with respect to x, we'll get 3x squared, right? And then this gives us 3y squared y dash. Now on the right side, we'll apply the product rule. Derivative of 6x is 6 times y plus 6x times y derivative, right? Now we need to isolate y dash, y prime. So let's bring all the terms together. On the left side, let me bring 6xy dash. So we have 3y square y dash minus 6xy prime. So y dash of y prime is the derivative of y. And we have 6y minus 3x squared, bringing 3x squared to the right. Taking y prime common, we get 3y squared minus 6x times y prime, that is 6y minus 3x squared. And now we can write the derivative of this function as 6y minus 3x squared divided by all this, which is 3y squared minus 6x. Right, so that becomes the derivative for the given function. We can of course divide everything by 3 to simplify, correct? So let's do that. So what I'll do here is that I'll rewrite the derivative by dividing everything by 3. So we have derivative of this function as 2y minus x squared over y squared minus 3x, correct? Or dividing by 3 we get 2x, sorry, 2x. So we divided everything by 3. 6 divided by 3 is 2, right? So we get 2 here and 1's there. So we have found the derivative of this function. So let's call this as our part A, right? So let this be the part A. Now let's do part B, which is find a tangent to the above at the point this. So we have the derivative as 2y minus x squared over y squared minus 2x. We need to find tangent at the point which is 3, 3. Substitute 3 and 3. So we get 2 times 3 minus 3 squared over 3 squared minus 2 times 3. So that gives you 6 minus 9 over 9 minus 6. And 6 minus 9 is minus 3. 9 minus 6 is plus 3. So we get minus 1 as the derivative. Now let me also share with you how this function graph will look like. So, okay, so let me draw it here itself. Okay, it's kind of, let's do it here. So the graph of this function actually looks like a leaf. So it's kind of like this. I should not say function, right? It is actually not a function, it's a relation, okay? So it looks like this. So that is kind of a leaf, which is the meaning of folium in Italian language. Now as you can see, the point 3, 3 actually is this corner. And at this corner, we just found the tangent line to be with minus 1, which is kind of like this. So that is the point P, which we are talking about, correct? Now we need to find points where the above tangent is horizontal. So basically, now in the next page, we'll work with the equation. We already have the derivative, which is 2y minus x squared over y squared minus 2x, correct? So now we are at the end of this video. We'll find the points where the tangent is horizontal. We already have the derivative, which is y prime is equals to 2y minus x squared divided by y squared minus 2x. So here is part C. We'll write down the derivative and then solve. So we have the derivative of this function as y prime equals to 2y minus x squared divided by y squared minus 2x. So derivative of x cubed plus y cubed equals to 6xy was found using implicit differentiation, and that's the result. Now when we want to find points where tangents are horizontal, That means what? That means y dash should be equal to 0, right? And that means that numerator, which is 2y minus x squared, should be equal to 0. Correct? Now 2y minus x squared equals to 0 means that y is equal to x squared divided by 2. Perfect. So we get a condition here from the numerator, y equals to x squared divided by 2. To find the values, or rather the points on the curve, we'll substitute this into the equation. So the equation given to us is x cubed plus y cubed equals to 6xy. Here we'll substitute x squared over 2 for y. So we get x cubed plus x squared by 2 whole cube equals to 6x times x squared by 2. So that can be written as x cubed plus 3 times 2 is 6 over 2 cube is 8 equals to 6x cubed over 2. Now this is basically 3x cubed, right? 6 divided by 2. So we can actually solve them. Bringing 3x cubed to the left side, we have x to the power of 6 over 8 plus x cubed minus 3x cubed equals to 0. And that is, let me take it to the right side and then further simplify. So we could write this as x to the power of 6 over 8 minus 2x cubed equal to 0. We can take x cubed by 8 as common, right? So let's take x cubed by 8 as common. So we get x cubed by 8 as common. So in that case, we'll get x cubed here minus, so since we took by 8, we have to multiply by 8 to get 16 here equals to 0. Now that gives us two solutions. This gives us two solutions. One is that x cubed is 0 or x equals to 0. The other one is that x equals to cube root of 16, right? 16 cube root. Now based on these two solutions, we can find y values. So if x is 0, let me write here, x is 0, it means y is what? So we know y is basically equal to x squared by 2. This is the substitution done. So if x is 0, y is equals to 0. So that is one point. Now the other one, let's write it in terms of 2. Since we have a factor of 2, it simplifies. So 16 is 2 to the power of 4. So we could write this as 4 over 3, correct? Okay. So if x is equals to 2 to the power of 4 over 3, then y is equals to 2 to the power of 4 over 3 whole square divided by 2, which is 2 to the power of 8 over 3 over 2, which is 2 to the power of 8 over 3 minus 1, correct? So 8 minus 3 is 5, so we get 2 to the power of 5 over 3. Perfect. So we actually get 2 points. So we can write on our answer as 0, 0, and the other point is 2 to the power of 4 over 3, and no, it is 2 to the power of 4 over 3, and y value is 2 to the power of 5 over 3. Correct? So that becomes the solution, or rather the points where the tangent line is 0 for us. Correct? So that is how we are going to solve it. Now some of you might have noticed that if I write 0, 0, y 0, x 0, we actually get indeterminate form. Do you see that? So note, for 0, 0, we get y dash equals to 0 over 0. However, we are saying that the horizontal tangent will be also at origin. So I'd like you to debate on this. Is it okay? So debate on this. Remember the curve which we're talking about looks like this. It's like a leaf here. So kind of like this. Is it okay? Kind of like this. So we do have seemingly to one this at origin, we do have a tangent line here whose slope is 0, but we also look at another line which is vertical, which you could see like this. Now it is not a function, it is a relation, so there's something more which we need to learn about, which we are not quite sure about at the moment since we haven't learned much. Second, we have learned about limits, where if the limits is kind 0 of 0, we may do something special. But at this stage, we are not very clear about it. So we'll go with this solution that there are 2 points on this curve where the tangent is horizontal. Is it okay? Okay. So that brings us to the end of this particular video, where we have learned what implicit differentiation is and its importance, and how we evolved it from the chain rules, basically extension of the chain rule. Perfect. I hope you liked this journey of understanding implicit derivatives. Feel free to share your opinions and views, and if you like and subscribe to my videos, that'd be great. Thank you and all the best.